Hello Math 1093, this is Dr. P with The Long Decline. So this is an application problem about a 90 milligram sample of strontium-90. You're probably wondering what strontium-90 is. That is a radioactive compound that over time decays. It undergoes something called beta decay, which means it loses a beta particle, and it goes from being strontium-90 to something else, another element called yttrium-90. Okay, not that you need to know all of that to understand this question. It's just the thing to understand is that strontium-90 is a radioactive compound that loses particles and turns into something else. So if we start with a 90 milligram sample of this stuff, over time, the amount of strontium-90 remaining is going to decrease. And in this problem situation, we're told that after 40 years, a very long time, the 90 milligrams has declined to 34.4 milligrams of SR90. And the question is, how much will be left after 100 years? Now, there's a couple of logical ways of thinking about this problem, but one of them actually reflects the science underneath what's going on here, and one of them doesn't. So let me first talk about an additive or linear way of thinking. Okay, so this is the additive or linear way of thinking. So over 40 years, we lose how much? 90 minus 34.4, which comes out to, I think, 55.6 milligrams of SR90. Okay, that's how much we lose. So the question is, how much will be left after 100 years? And I actually mean 100 years from this starting time, not 100 years after the 40 years. So over 100 years, how much will we lose? So we might say that if we lost 55.6 milligrams over 40 years, then that's a loss rate of, let's use my calculator, 55.6 over 40, that is 1.39 milligrams per year. 1.39 milligrams per year. So you might say over 100 years, you would lose 1.39 milligrams per year times 100 years, which comes out to 139 milligrams. But wait a minute, we started with 90 milligrams. So how in the world are we going to lose 139 milligrams? This is impossible. Okay, so that's just an illustration of the fact that this way of thinking doesn't really make sense for the situation we're given. And it actually doesn't really model what's going on anyway. Because when we have a sample of strontium-90, what happens is some percentage of that each year is going to decay into yttrium-90. And it's based on a percentage. So if you have a 90 milligram sample, some percentage of that is going to go away after 1 year. Like maybe it's a milligram, maybe it's 2 milligrams, whatever. But if you started with a larger sample, you would lose the same percentage, which would be a larger actual amount in milligrams. Okay, so this additive linear way of thinking doesn't reflect the fact that you don't actually have a constant number of milligrams lost per year. What you do have is a constant percentage lost per year. And for situations like that, we need a multiplicative or exponential way of thinking. So let's see what that would look like. All right, so one way of building this, so the whole idea of this problem is that we have this sample of strontium-90, and we have some scant information about what happens to it. If we want to know how much is left after 100 years, one way of finding out is to build a formula. Build a formula for f of t, the number of milligrams left after t years. So we need to build a formula for f of t. All right, the way that that formula is going to look, it's going to be f of t equals some initial amount, which we already know what that is, times e to the kt. This is a formula that can capture any function that describes exponential growth or decay. We can always use a base of e. We could also use other bases if we wanted to, like we could use a base of 2, we could use a base of 10 if we wanted to. Any base would work. We just have to commit to one and then figure out what this coefficient is going to be. All right, we already know that this is the initial value. The initial value is 90 milligrams. So we know that A is 90. And we also know that F of 40, the amount of strontium-90 remaining after 40 years, that's known to be 34.4. So I'm going to use this information here and the fact that A is 90 to try and figure out what the parameter K is equal to. All right. So I'm going to do that by substituting this point into my formula. So I have F of 40 equals 34.4, and then substituting the formula that gives me F of 40, I get 90 times e to the kt, e to the k, where t is 40, is equal to 34.4. Okay, so this is because t is 40, this is because a is 90. All right, so what do we know? We know that e to the 40k has to be equal to 34.4 divided by 90. I'm just dividing both sides of my equation by 90. And then if I want to unwrap what k is, then I need to somehow get rid of this exponential here. I need to get rid of this e to the. How do I get rid of e to the? With a natural log. So I'm going to take the natural log of each side. Natural log of that equals natural log of this. So the natural log of e to something is just that thing. Natural log and base e exponential are inverse functions. So 40k is equal to the natural log of 34.4 over 90. So k is equal to 1/40th of natural log of 34.4 over 90. And according to my calculator, that gives me, let's see, 1/40th times natural log 34.4 over 90. I get negative 0.024. Negative 0.024. So I now know a formula for f of t. F of t is going to be 90 times e to the negative 0.024 times t. And that will tell me the amount of strontium-90 left at any given time, t in years after I've started measuring. All right. One thing you might notice from that, by the way, based on the previous video, this tells me that I have a constant decay rate of negative 2.4%. I always record that negative there just because that reminds me that this is a decay rate, not a growth rate. But anyway, that's not really what we were here to do. We were here to find how much is left after 100 years. So we can now substitute t equals 100. I get 90 times e to the negative 0.024 times 100. And let's run that through the old calculator here. 90 times e to the negative 0.024 times 100. And I get 8.164. I'm just going to round that to 8.16. So I have 8.16 milligrams left after 100 years. Okay, so the whole point of this video is just given a trace amount of information about this radioactive compound, if I just know what its initial value is and its value at some other time, in this case 40 years, I can use that to build an exponential model for how much of that compound will be, or not compound, I guess it's like how much of that substance will be left after t years. Okay, so I develop a formula using this template. I can always do this using an initial value times e to the kt, and then I use algebra to solve for what k is. For this, I have to use one of the given points. That a is just the initial value, and then once I have this formula, I can just substitute in any value of t that I like. Now also, if this question had said not how much is left after 100 years, but say how much time would it take for the amount of strontium-90 to go down to, let's say, 2 milligrams, I could have done that too. That's just sort of the inverse problem of this. In that case, I would take this formula here, sorry, not that formula, this formula, and I would set f of t equal to 2 milligrams, and then use the same sort of process I used earlier to solve for t. So this creates kind of a nice, versatile process for solving problems about exponential growth and decay.